Alright, first problem. The two guide rails for the elevator shown above each exert a constant friction force of 100 newtons on the elevator car when the elevator car is moving upward with an acceleration of 2 meters per second squared. The pulley has negligible friction and mass. Assume g equals 10 meters per second squared. Okay. On the diagram below, draw and label all forces acting on the elevator car. Identify the source of each force. Seems easy enough. So the elevator car has a weight force on it. Looking at the car, there's a cable here. So that means there's a tension. And the problem says that when the elevator moves up, so if it has an upward velocity, there is a force of friction from each guide rail. So FF, trying to make those straight down, FF. And it says from each, so that means there's two. Now the problem asks me to tell the source of each force. So tension comes from the cable. Friction from what it called the guide rails. And gravity, or weight, from, not equals, from gravity. That's where each force comes from. Alright, part A done. Calculate the tension in the cable lifting the 400 kilogram elevator car during an upward acceleration of 2 meters per second squared. So I'm asked about a force, whoops, need my pen. Asked about a force and told an acceleration. So that's an F net problem. Alright, there are two objects, so it's possible we might have to do F net for elevator 1. I'll switch to doing that in blue, or object 1, and F net for the counterweight, and we could call that object 2. But let's see. We know the acceleration for the object, we know its mass. Let's find out what forces are on it real fast. So it has tension, and we've got to decide a coordinate system, so let's pause for a second here. Why don't we, since the elevator is going to move up, call up positive y and down negative y. So tension points up, that would be positive. Whoops. Tension points up, that's positive. Gravity points down, it's negative. There's a friction down and another friction down. And that all equals to the mass of the elevator, what we've called object 1, times its acceleration. Okay. We know this thing will accelerate up, upward acceleration, so this term here will be positive. And then if we use the other object, it will be negative, because if one of them goes up, the other has to go down. Okay. We said earlier we know acceleration and mass. We know FF. The problem says each one's 100. If we know the mass of the elevator car, which we do, we can find its gravity, or its weight. I should stop calling that gravity. Its weight or force of gravity. So the only thing we don't know is the tension. Okay. So I don't think we're going to need to use the other object, because right now we only have one unknown thing, and we have one equation. So we can solve for that one unknown thing. I'm going to do two things. I'm going to change Fg to Mg, and I'm going to move everything that's not tension to one side of the equation. So I'm going to add Fg and FF and FF. So I get tension equals mass 1 times A, which is just this here, plus Fg, which I'm going to go ahead and turn into M1g, plus FF plus FF. There we go. So let's plug in numbers. Tension equals 400 kilograms, that's the mass from the problem right here, times 2 meters per second squared, plus 400 kilograms times 10 newtons per kilogram, gravity, plus 100 newtons for the first friction, plus 100 newtons for the second friction. All right. 400 times 200 over here, 400 times 2 will be 800 newtons. 400 times 10 will be 4 4,000 newtons. So we now have 800 plus 4,000, that's 4,800, plus another 100, that's 4,900, plus another 100, that's 5,000. So tension is 5,000 newtons equals tension. All right, found that, check. On to part C. Calculate the mass m the counterweight must have to raise the elevator car with an acceleration of 2 meters per second squared. Okay, well, let's scroll back up and look at the counterweight, see what that is. So the problem says that this thing here is the counterweight, and let's look at the forces on it. It's not touching the walls, so it's not going to have the friction like the elevator car did, but gravity will pull it down, so it has weight, and it has tension. And since there's only one cable, it'll have the same tension as the other car. So let's scroll back down, and I'll redraw the free body diagram so we can refer to it as we go. This car has its weight, and it has a tension. And until we find the mass, we're calling it big M, according to the problem. This problem involves acceleration. We're looking at forces, so this is an F net equals ma. Okay, let's use the same coordinate system just for simplicity as we did before. Up will be positive y. We currently know the acceleration, it's 2 meters per second squared according to the problem. Let's list all our forces and then see if we have enough info to find m. And I should really call that big M because the problem calls the mass big M. So that'd be big M. Our forces are tension, which is up, so positive, and minus Fg equals mass big M. That's what the problem calls it, big M right here, capital M, times the acceleration. If I change Fg to mg, I can easily find the number for it. So tension minus mg equals ma. Oh, and you know what? Earlier, we said that the elevator car, so if we think about the picture of the problem, we've got the car, we've got a pulley, we've got the counterweight. We said the car would go up, meaning the counterweight goes down. So its acceleration is negative. So this should be negative, 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 because the acceleration goes down for the counterweight when the elevator car goes up. They're attached by a string over a pulley. If one goes up, the other has to go down. Now we've clarified that. Let's move all the m's to one side. So I'll add big mg, and I'll get tension equals negative ma for the reasons we just discussed. Remember, this term is negative because the counterweight goes down when the elevator goes up. Negative ma plus big mg. And by big M, I'm just saying that instead of capital M. We need to know the mass. Right now the mass is attached to both acceleration and gravity, so let's factor out mass. T equals big M times negative a plus g. I factored out positive big M, leaving the a in the first term negative, leaving the g in the second term positive. If I'm solving for m, I got to divide by what it's multiplied by, so negative a plus g, negative a plus g. Let's bring this up here for the sake of space. We now have tension over negative a plus g equals big M. We know from the last problem that our tension up here in the right corner is 5,000 newtons. We know A is 2 meters per second squared, and we know the problem said assume on Earth G is 10 meters per second squared. So, tension over I was going to do that slower. Let's just go ahead and fill in the numbers. So let's skip rewriting it. 5,000 newtons for tension. 2 meters per second squared for A. 10 newtons per kilogram for G. And meters per second squared and newtons per kilogram are really the same unit. All equals big M. Negative 2 plus 10 is 8. So it's 8 meters per second squared on the bottom. 5,000 divided by 8. If you want to grab a calculator and do it yourself real fast, I'll pause. 5,000 divided by 8 is 625 kilograms equals capital M. And that is the mass of the counterweight. All right. Things that might trip you up. If you're wondering what I was about to do here, for some reason in my head I just wanted to rewrite the problem, but I'd already done that here. So that step was not important. I would just copy it down again. So instead I just went ahead and plugged in the numbers, divided, or added and then divided, got 625 kilograms equals mass big M. All right, that's the end of problem 1. When you're ready, move on to problem 2.